All right, so moving along with the agenda, our next speaker is a computer research scientist and project manager at RNet Technologies, and he's working on several projects in high-performance computing, big data science, and networking. He's currently developing new methodologies to more efficiently load data in HPCC. So please welcome Mohammad Rashti.
Good afternoon, everybody. Hope everybody had a good lunch and got some energy and ready to have some sleep. So I'm going to talk about some little bit technical, maybe stuff that might help you for that. And so the project that we're working on right now is improving data loading in Thor cluster using parallel direct spraying into the Thor nodes. So basically, this is not a use case of HPCC. This is rather a more HPCC development that will hopefully improve some current use cases and will enable some future use cases. So the outline of the presentation, quickly I'll talk about the data loading, how it happens, and then the potential optimizations that we are thinking of. The overall module that we are working on, and it can partially be applied for the data loading in Thor, is called Informer. This is part of an SBIR project, Small Business Innovative Research, that is funded by the government. And so I'll talk about, briefly talk about the details of that, and then particularly the case that we are covering right now, that's loading data on HPCC deployments on Amazon Cloud. And then quickly go over the future work. So data loading in HPCC, basically it's talking about the backend or the Thor cluster, which is the data refinery. In Thor, the data needs to be transferred into, original data that is going to be imported needs to be transferred to the drop zone or a landing zone. And from there, it gets sprayed over your Thor nodes to get us started with your refining and analysis algorithms over there. There are cases that this might cause some overhead because you need to drop it in that zone, and for some cases that's going to have some performance issues. And so we're trying to see if we can improve that. That especially happens with large data sets, and also some cases that if you want to do a partial data load, so this could help by applying that reduction right at the time that you are loading your data, rather than loading the entire data and then doing the reduction. So the approach that we're taking is to basically remove the bottleneck in the landing zone by reading the data records directly into the Thor in a parallel fashion directly from their original data format, and basically in a distributed manner. Every node, the ultimate goal is that every node reads its own data that needs to load it, rather than doing the spraying, which is a shuffling operation doing there. And after that, we're also planning on having in-memory processing, so basically skipping some even disk trips. That's a longer goal, so I'm not going to talk about that into details. So as I said, the name of this module or tool set is Informer. I'm going to give some quick introduction to what an SBIR is. SBIR projects are funded by the government. This one is by the Department of Energy to promote big data processing in the commercial world. There are two phases. We are currently in phase 1, which usually takes 9 months. We're about 5-6 months into it. And phase 1 includes some feasibility study and potential commercialization study of that, and then designing the actual overall prototype. And then phase 2 is the prototype completion, commercialization of the product, and then for that we need a new proposal. So our current phase is going to end soon, and then the second phase is in 2015. Informer, as I said, is the ultimate product. So the product that we're working on is going to have two distinct functionalities, hopefully added to the HPCC. One is an efficient batch and in situ data analysis. So basically, both batch and streaming and in situ data analysis. And then the second one, which is the focus of the presentation, is low overhead native format data access, basically trying to access the data directly from their original source without doing that copy. So here we show how this will fit into the HPCC. So the first part, which is called mate, would be able to be integrated into the Thor cluster, and the second part, which is again the focus of this presentation, is going to be in the back end for loading data. So this is a very simple representation. It doesn't have anything to do with, it's not going to very details. So that mate part that I was talking about is originally meant to replace MapReduce. So it was developed in the Ohio State University that we are partnering with to transfer the technology. And so it uses the concept of reduction object where the data is getting reduced in place and without requiring those key value exchanges that is usually done in the MapReduce. So this is an alternative to MapReduce. I know HPCC is not using MapReduce, but this is particularly designed for some use cases that could be very helpful for them, especially the scientific data analysis, because that's coming from the university who are working on scientific data. So that could be a very good complementary to the approach that exists in HPCC. So using that reduction object, it has been shown to improve the performance of the analysis between 1.5 to 20 times compared to the MapReduce. The second part, which is the virtual data integrator, is what we're talking about right now mostly, is offering an API that will allow you to directly load your data from any file system or format into your system, like into the Thor cluster, for example. So different file systems and different file formats, particularly, is focused on these scientific data formats. So why on the scientific data formats? Because in the scientific world, and like in the DOE national labs or scientific experiments, there's a huge amount of data being generated real time. And sometimes, like for example, in synchrotron particle accelerators, they get like gigabytes of data per second, and they put them in these formats. So for example, that case that I said is an HDF format. Data is a kind of a matrix type of data, and there's no way they can transform that into any other file system for processing for two reasons. One is that the data is huge, and second, and probably they don't have that much of the resources. Second, the data is being generated real time. So what happens is that if you want to like have Hadoop or even spraying into the Thor, the data is going to go obsolete or you're going to be overwhelmed by the data. So you need something to quickly load the data directly from their original file, put it into the memory, into the Thor, rather than doing that spraying. So this VDI has two parts that we have designed and working on implementing. Has a data storage adapter section and an API section. You can see here, it directly goes with your original stored data. There are adapters for different file types. You enable one of them to read from your current file type, and there is a fixed API that makes your program not change for every data type. So basically with that, you can skip this step of putting it into the DFS and directly load it into the memory. So I just talked about those, so I think I'm not gonna, yeah, so one point for that adapter section is that it allows you to make a partial data load. That is partially implemented right now, not integrated into the Thor or anything. So basically, you can load part of your data directly from their source rather than loading your entire data, which is very important, especially for the case that I said. So they're talking about on the, let's go to the example that I brought. So you have your particle accelerator detectors. There's a camera at the end of it that is going to detect those particles that are passing through the material or getting accelerated. In that case, you need to only load part of the data that you plan to work on. So maybe some columns in a strided form, or a piece of that image that is more interesting for you, or that type of thing, which is, this is something that will help with that. Some internals of that module. So basically, you have different adapter modules here implemented. The data is being passed through those, and then you can have a strategy of full read or partial read of your data. The API section is just a unified API that is disguising that complexity from the user, so, or from the implementer who is actually programming that for you. So there are well-defined hooks that can have any type of data, and we will have some pre-implemented file system and format adapters for that. Okay, so that was a very quick introduction to the whole big picture. And for the particular case on the HPCC on Amazon Web Services, we are trying to do efficient loading of the data that are residing on a simple storage system, or S3, on AWS. Particularly, the files that we are targeting are compressed files that include multiple XML records in them, or multiple XML files, each file including like thousands of records. So what we're going to do, and we have been working on, is a distributed operation on those files, basically loading, decompressing, and spraying off those files, or putting them into the memory where they need to be, and on the disk if that's what's desired. So first step that we do is still includes some shuffling of the data, but eventually we're going to get rid of that as well. So this is the process that is currently being done. So the file being loaded from the S3 on the landing zone, and it's decompressed. So basically, you have a file, multiple XML files inside it, your archive, and then be put on the Thor cluster. That Thor cluster is residing on the EC2 on AWS. The current approach that we are taking is to do a parallel load and on-the-fly decompression of the data, and then extraction of the records, and either direct them to a Kafka-based distributed file system sprayer that exists with the HPCC right now, or directly put them to the through a custom module to the Thor memory. So at this point, we're currently working on approach 2, and then we'll go to the approach 1 after that. First step of the development has been to first distribute the landing zone and the spraying. So we've currently implemented the operation of parallel load decompression, and spraying of the XML files from S3. And then each node on the Thor, so instead of having one node doing that, so you have multiple nodes that directly connect to S3, read your records, XML records, and files, XML files from that archive and decompress them, and then put them on their own node. And then, because those files need to be distributed, we have a distributed spraying happening at the end. We are load balancing those operations to make sure that everything is happening in the most optimized way. And we're using a library called Message Passing Interface, or MPI. Most of you might be familiar with it, for the communication. The step 2 will be to skip that communication altogether so that everybody is just doing a completely data parallel operation where you can directly load your records on yourself without requiring any extra communication. So this is what's happening right now. There is a multi-file zip archive. Multiple nodes do that, decompress, and do the shuffling at the end. Some preliminary numbers on what we have seen so far on implementing this. So these are 3 graphs that are similar because they are the results on using multiple, like different file sizes, loading different file sizes, 160 meg, 640 meg, and 1 gigabyte. So don't go into too much details there. I'll explain everything here. So what happens is that we have listed all the different steps that happening in the operation and have compared the case that you use the single landing zone versus the distributed spraying. In this test case, we have used 4 nodes on the EC2, so we have 4 Thor nodes that are performing the operation. And for example, here in the 1 gigabyte data case, these are the steps. So first you load the data from S3, decompress in distributed way, do your shuffle or spraying, and then there's some overhead, miscellaneous overhead, and then your total. So the blue ones are the current one, and the sequential landing zone, and the red ones are the distributed case. So as you can see, in all cases, the S3 load and the decompression are seeing almost linear speed up, which is helping to reduce that time. And then there is third step that is shuffling that data, which is a little bit high here compared to the others, and doesn't see that much of the speed up as the others see based on the number. The numbers are not, you don't see the raw numbers, but from the graph. The reason is that in general, the operation of all-to-all exchange is an expensive operation and is not really scalable. So we are going in the next immediate step to remove this altogether, which is going to save us a lot. And then hopefully this total improvement will go up. Okay, so my last slide is the next steps that we have. So there's a few immediate steps that we're doing at this phase of the work, which is to complete the operation, make sure that, so currently we are spraying to the Thor. We just want to make sure that in the code that all these records are getting on the disk correctly. So that's one correction step that we're going to take. And then we're going to have more data sets to make sure that it applies to different data sets here and works well and is smooth. And then we will, that's what I talked about, eliminate that scattering, which is a big chunk of the time, and further improve that into super linear, hopefully, speed up. And then we will integrate this module into our big picture of the virtual data integrator, and then have other modules develop after that. So in the second phase, we'll hopefully make sure that things get integrated into the HPCC version, and we're also thinking of in-memory spraying and data processing as a new feature to be added. So, any questions? Sorry?
Do you have any plans to support spraying data from S3 that is not in zip files? So if I have a bucket with a number of folders in it, and each folder has anywhere from tens to hundreds of thousands of individual XML files, and I want to spray them in a distributed fashion?
Yeah, this, I mean, the whole architecture can support that as well. It's just that you need to have the underlying module that deals with that particular case. In this case that I discussed, because it's an imminent problem that we have been talking about with people, we are looking at a compressed file. But yes, I mean, you can tweak that module and have a new one that can look at those type of files.
Any idea when you'll have something available for consumption by others?
I can't have an estimate about that right now, like on the stage.
Okay, thanks.
That's okay, we have your phone number.
Yeah, sure.
If you're around the UK.
I think somebody over there had a question.
In the process, you mentioned you're going to put the data directly on the Thor nodes. Are you going to be running like your own code or processes on the Thor nodes, or are you going to be trying to integrate with the current Thor slaves to put the data, or are you just going to put it directly into the disk in the Thor format?
We are currently putting it directly onto the disk in Thor format.
Regarding data lineage and versioning, this may be a more fundamental question, just trying to understand as you ingest the data, right? Do you keep track of the data sets and the versions of the data sets, or are they more isolated? And do you keep track of the lineage? Just wanted to understand.
No, I think that will be very important in the next step, especially if you want to have the, are you talking about like fault tolerance type of reason for that, having that lineage? I mean,
No,
is there a...
Not necessarily. As you start doing analysis, right, and then you have a question in terms of the results of the analysis, right? Then a lot of the times you want to go back and see, I was expecting this, but then the results are very different. You might want to go back and see all the way back to the source data set, right? So from that perspective, I wanted to understand.
No, we're not. We haven't looked into that yet.
Okay, thank you.
So he hasn't.
What about the metadata, like talking to DALI, or, I mean, you're putting the files on the Thor nodes, but the metadata and how DALI and the whole cluster knows about a file is made up of all these components. I didn't see any step there where you're embedding that metadata or changing it in DALI about the new file.
Well, no, we're not. I mean, we're dealing with the with actually loading the actual data. I mean, so that is not a bottleneck for this particular process.
So later on, you just use a regular DALI just to tell it, and the files are already there somehow.
Maybe I'm not completely understanding the question.
We can take it offline. That's fine. Thank you.
Sorry.
It's a little bit more details. Probably
Sure.
I'm not understanding the exact process of how the cluster becomes aware of the file. I mean, I know you put it on disk, but there's a bigger picture to the file to the HPCC
So you need
have
to
knowledge that the
define.
file is there somehow.
Yeah. So the spraying process, as part of the spraying process, you need to define that logical file that points to all those sprayed pieces on the different nodes. So we're not doing anything to that. I mean, we're not changing that because that's still happening on a distributed system. It's just how you load your data from S3 and then, or from any format that cannot be put on one node. It's going to be a big bottleneck if you put it on like a landing zone. So any other question? Oh, okay.
Where would we go to follow the development? Let's say phase 1 gets done. How would we know that occurs? Where do we find out?
It's like we haven't yet wrapped this stage. So once we wrap this stage and so do all the necessary testing and integration, we'll put it on the community for access.
Okay, so you showed some a benchmark on your XML data. Are the numbers similar for the other formats that you've discovered, or have you run tests on those to find out what those are yet?
No, we have not yet. Yeah. So I mean, we're focusing on XML right now, but given the fact that this is going to be designed for different file formats to support, I mean, that's what it claims, right? So hopefully we'll have those as well. Any other question? Okay. All right. Thank you very much.
Good show.
Thank you.
Thanks, Mohammed. It's interesting to see the role HPCC is playing the SBIR project and other just different industry, Department of Energy. So we'll look forward to hearing about the 2014 phase 1 and hopefully phase 2 next year, right? Our next speakers come to us from one of the earliest adopters in the world of academia, Florida Atlantic University in Boca Raton, down the street from our Boca Raton office. We've got 3 speakers. Borko Furht, professor in Department of Electrical and Computer Engineering and Computer Science at FAU, founder and editor-in-chief of the Journal of Multimedia Tools and Applications, and I could go on and on.
And Journal of Big Data also.
Yes, and recently co-founded the Journal of Big Data also.
Yeah.
Thank you.
This is important.
Also, after Borko, we'll have Victor Herrera coming up. He's a PhD candidate and research assistant at FAU, who's done a lot of collaboration with LexisNexis and machine learning. And finally, LexisNexis' own Edin Muharemagic. Edin serves as the data scientist for Risk Solutions and has also taught a class at FAU on data-intensive computing. So I give you the gentleman of FAU.
Okay.
Thanks.
Ken, how do I change slides? Probably this one, right?
Yeah, that's it. Just use this button up there.
Okay. Good afternoon. We have 3 presentations. My presentation will be general. You can see the title, LexisNexis FAU Success Story. We started working with LexisNexis because we are neighbors for probably last 10 years in different categories, publishing papers, books, research projects. And then after me, our PhD student Victor and Edin, who is supervising him from LexisNexis, will tell you more specific about the projects that we are doing for last 2 or 3 years. First of all, I will tell you more about university and about our department and about our center. Why? Because LexisNexis is the first member of this center, which is now one of the very powerful centers in the United States. So I will tell you about this as well. let me talk first about the companies. You know better than me. I was in the industry as well. Why some companies are successful. And I put several on the first slide. I have another on the next slide that I'm not going to tell you yet. Apple, Amazon, Google. Apple, we all follow what happened with the Apple. Apple was in big trouble. Steve Jobs came back and redefined mobile system and entertainment. What he did, if you remember, he changed the name from Apple Computers to Apple. And then, of course, he moved from computer business to phone business, mobile phone business, iPad, and everything else. I'll never forget 2006. I'm talking about the next company, Amazon. I go every year to MIT. MIT has a phenomenal conference that I will suggest to industry people, and there are mostly industry people attending emerging technology every September, October, and they invite leading entrepreneurs. And at that time, 2006, was a person from Amazon, a French person, and he said, I'm CTO, and it was this kind of room with about 500 people, and he asked, what do you think what we are doing, Amazon? And the guy in the first row said, I know, you are selling books. He said, yes, we are selling books, but I have 1,000 computer scientists in my division. We are doing something else. What you are doing, we are building cloud computers. Anybody knows what a cloud computer is? Nobody raised a hand 2006. If I ask now, I don't want to ask you, everybody will probably raise the hand. So they came up also with out-of-box thinking, and today Amazon, as you know, is one of the leaders, and there are many others after Amazon, but they did also, they changed, I call this redefined computing with cloud computing. Google, we don't need to talk too much about Google. Google redefined search on the internet and much more. I would look at as LexisNexis redefining, if you will, data analytics and big data. And because I'm following LexisNexis for all these years, I would think that LexisNexis is one of the leaders in this field. Unfortunately, when I talk with people, when I go to MIT, when I go to different big conferences, I mention LexisNexis very often. They immediately ask you, are you talking about Lexus cars? In other words, something is missing how to promote, and you know probably better than me, how that LexisNexis or something, or HPCC or something else, becomes name that when somebody mentioned, like I mentioned Google, everybody knows. Yahoo, no. Now even Alibaba. Suddenly Alibaba, we knew just the stories. Now everybody knows about Alibaba. So I believe that promotion has to be done probably better. So when somebody mentioned LexisNexis, they already know we are talking about big data analytics and these kind of things, that LexisNexis is one of the leaders. Okay, a little bit about our university. We knew all this and we are following. So we said we are redefining education. And many people who are working with us, they know that we are redefining education. And we are not the only university. There are many universities redefining education. How you redefine education? You build so-called entrepreneurial university. In the past, I've been at universities many years. I was also in the industry. In the past, university was completely out of industry, entrepreneurship, companies, etc., etc. They were just training students. They got diploma. They go. You don't see any executives from the companies. You don't think about startup companies very rarely. Today, you cannot survive as a university if you think in this way, specifically engineering schools, and we are here all in engineering field. First of all, here are a few things that we are doing for a number of years, I would say 5 to 10 years. We are following technology trends. Here are the number of trends that we have to teach. In the past, it was up to professors. If my field is X let's say, parallel computing, I teach this forever, and nobody needs anymore. Or we need parallel computing, but in different ways. Now we force us, professors, to teach. You can see on the left-hand side all kind of new classes that we are teaching today and which are part of the hot areas in industry. Second, we are creating some interdisciplinary programs. Today you cannot have only engineering. You have to do management, you have to do entertainment, bioengineering. These are all new programs at FAU. We are offering hot courses based on these new technology trends. I'm proud to say we go to industry and find the experts. And just 2 or 3 years ago, Dr. Edin Muharemagic, who was our student and got PhD at FAU, he was teaching very popular data-intensive computing class. What he was teaching? HPCC. We created HPCC on our computers at FAU. There were about 18 graduate students. I attended several classes, specifically the last several, when students presented projects. Every student in the class presented a HPCC project. It was very impressive for me to see how they use now and speed up all these data analytics programs. And you can see many other. iPhone programming, we have here Julie Carmignani, who was our student as well, who got job at LexisNexis, who was teaching the class for 2 years on iPhone or mobile development because she learned how to do this, so she was expert in this. And you can see many other classes like game programming, social networks, cloud computing, and many others. Here is the other details of our model of entrepreneurial university. First of all, I will focus on the first sentence. It's clear: drastic reduction of industry research funding. We all remember Bell Labs, we all remember IBM Labs, which still exist, but they are not doing really too much research. They are doing very applied research. This was a chance for universities. So United States and NSF, National Science Foundation, found out that this is a clear chance for university. They started a program about 10 years ago called, on the right-hand side, Industry University Cooperative Research Center, and our center is called for Advanced Knowledge Enablement. The name was selected carefully to cover exactly what you're doing and many other companies: big data analytics, cloud computing, data mining, and many other areas which have to do something with knowledge enablement. We got a grant from NSF 5 years ago. Guess who was the first member of the center? LexisNexis. And you are still the member. Your membership means budget for several projects that we already had in the past, number of publications, and this is what Edin and Victor will talk a few minutes after me. Not only that, we are lucky at FAU, and Boca Raton people from LexisNexis probably know, probably don't know. At FAU, because it's a big university, there is a research park with close to 50 companies. There are 27 companies plus 23 in incubators, smaller companies. And our department, our center works practically with all these companies. Works in different ways. With some, we work on the projects. With some others, we provide students, interns, and so on. So it's very nice on the picture on the left to see companies close to us. LexisNexis is almost there because we just crossed the street, and we are there, and I visited LexisNexis in Boca many times. We have a strong and active industry advisory board. Flavio is a member. We have a meeting on 23rd and 24th, and Flavio will serve as the chair of the board for that meeting. President of FAU will be there, and 3 program directors from NSF. So it's going to be a very active meeting where, again, LexisNexis will show the leadership among the industry members. Here is how the center works. This is what NSF invented. There are 55 universities, members of this center, only 15 in our field. Our field is computer science and information science. So we got, jointly with FIU in Miami, this grant 5 years ago. Companies provide membership. This membership is not because we have nice blue eyes or we are good athletes. No, this is membership is for real projects, applied projects. So the members of the center, they propose the project at the meetings, and then we vote, not we, companies vote, and then we work on the projects. I'm proud to say that today we have 29 members. Some of them joined and probably didn't come this year, but here you can see the list. LexisNexis is again #1, and then many other companies. Many of them are startups, small companies. There are several big companies, including even Google. Motorola Mobility from Plantation was acquired by Google. So Google became a member of the center 2 years ago, and they gave us a nice membership to develop mobile application. Guess for what system? You would say for Android. No, for iPhone. Why? Because they said, we can develop for Android. You need to develop for us for Android and for iPhone. And we were successfully developed several former Motorola applications for Google. In the meantime, unfortunately, Google sold Motorola Mobility to Lenovo, China. They're still members, so now we are saying we have a member Lenovo China in our center, but basically their membership will expire very soon. So you can see this list. Here is how it looks like, the meetings that we have at FAU. We have a new green building with lots of labs. We get together, we discuss the project, we present the project, something very similar what you are doing here. But here we are talking about university, industry collaboration, and how we can provide. I always say we are right hand, we are extended labs for the company. Here are the building and a few labs. We have 9 research labs, all available for this kind of projects, and 6 instructional labs where we teach not only computer languages, but also we teach mobile programming, hardware design, chip design, etc. We have, you can see it's mobile system development where Julie, who is here among us, was teaching the class. And you can see multimedia labs, so 9 research and 6 instructional labs. We have a cloud computing center on the first floor, not in the cloud, which runs all this. This is a research park with 27 companies and 24 additional companies in the incubator, occupying probably about 10 to 12 buildings in the back of the campus, probably on the walking distance. We have a collaboration with United Nations. Last year, we were asked, and I brought a number of industry members to have a forum building public-private partnership for education through science, technology, and innovation. So we were invited, and this was May last year in New York. Here is the project. I will show you several projects. I'm not going to steal the show. I have a few more minutes, right? I will not steal the show from Edin and Victor, but this is a project that we are doing with LexisNexis at this time. I think this is the second or third project that we are already doing, developing machine learning algorithms. And here is the research team, Dr. Tage Koškoftar, who is a very established researcher in the field of machine learning and data mining. Here are a few other projects that we've completed exactly 30 projects in the last 5 years. Here is a successful project that we did. The title is Distributed Cloud Computing Study to provide 3D visualization services for climate data on demand, for hurricane type, for tornadoes, and so on. So we developed these models, and it was this NSF selected this project as a industry-nominated technology breakthrough. Our goal is always to have a set of projects that we can propose to NSF, and they published the book on the left-hand side. This was the latest book from 2014, where we have about 3 projects. My goal, my objective, jointly with Flavio and everybody else, is to put at least one LexisNexis FAU project in the next booklet. This booklet is sent by NSF. This is the only booklet sent to all congressmen and senators. They send this booklet, which has inside probably about 50 breakthroughs from different universities. On the first page was Berkeley, and then Stanford, and then FAU has also 3 projects in the book. So they send to senators and congressmen. Of course, they always say in NSF people, and then we ask for more money. And then, of course, because of this, probably they get it. So our goal, our joint goal should be that one of the projects, maybe machine learning algorithms and HPCC, we can put for the next book. So you can then, this is a phenomenal promotion. Then you can, not only senator and congressmen will learn about HPCC, but also we can have this book for your future customers. This is another project that we did in the field of video processing for a big company, Emerson. You probably all heard for Emerson. They have a division, Avocent, in Florida. And it's, again, by the way, this project was also industry breakthrough. In this project, we created a special image processing algorithms to identify assets, or let's call, asset in these racks. Why? Because this is for the maintenance purposes. Why? Because then once when you have an iPad, and we developed all this, you can just point the iPad, identify the asset, get the architecture, and not only architecture from the database and clouds, you get also information about this. If something is wrong, the current, the capacitor, the measurements, etc. So we created this last year. They presented, their CTO presented in Chicago to the whole company. This company has, I believe, more than 10,000 people, and now they're using for maintaining all these assets that they have. Here is Julie's project that I'm proud to also mention. She was a master's student. She developed on iPad 2 applications. We call this augmented reality methods for hearing augmentation. We even wrote a chapter for the book based on this, where this is exactly from the iPad. I was pointing to her. And the first application was for deaf people, where you point to the, I'm a deaf person, I point to the person who is talking, and I can get immediately speech to text translation, and I can see this. We never commercialize this. This is a goal to commercialize because of the limited vocabulary. The second application is for everybody, not only for handicapped people. It's translation. You select the language. You are in France, in the restaurant. The waiter comes and tells you something in French, something bad. You point to the waiter, and you immediately get translation. Then you can answer also with the bad words. So these are 2 excellent things that Julie did several years ago before this was her master thesis. The newest project that we are just finishing now, we have a patent pending on this, is to identify a driver who is driving and who is sleepy. It happened, I assume, to everybody. If you drive on the long distance or in the evening and you have few drinks, and then you fall asleep for 3 seconds. So we are designing now the algorithm. It was already designed by our PhD student. He's defending PhD, by the way, October 26th. And based on the camera, it looks at your movement, your eyes, and then immediately starts the alarm. So the driver can, in a matter of milliseconds, wake up and save the life. And we found statistics that drowsiness causes 7% of all road accidents and may to blame a full 18% of fatal collisions. Some car companies we found out, like Mercedes and Lexus, they're trying to do something, but yet they don't have a good solutions for this. So this would be fantastic commercial solution. I'm going to skip this because I'm limited with time. This is a project that related to identification, reconstruction of the in image processing of the brain cells for Max Planck. This is about smart building design. And my last slide, just a message that most of you already know who are working with us, that we like to serve as extended research development arm for industry members. And LexisNexis is the best example. We have the lab where our students work, where Edin comes and visit them, or anybody else. Flavio was several times there. Work with current members and attract new members. Prepare and submit joint research proposals. This is what we did with some other companies. We are planning to do with LexisNexis. This is a very good alternative. We write proposal, but on the topic of LexisNexis, we send to NSF or any other government agency. And then once when we get funding, and the funding it's usually very high probability to get through this center, then we jointly work on this project with somebody else's money, with government money, instead LexisNexis paying or somebody else. So this is my next objective in next few months, to find a very good topic that we can write together, proposal and FAU and LexisNexis. Produce joint publication, presentation, and books. We already did many. We should do more. I learned from my previous job when I was vice president of Modcomp in Fort Lauderdale, a computer company. We were publishing lots of books and papers and everything else, and it helped us a lot to show, to promote our, we built the first, at that time, real-time Unix system, and we wrote the book, and everybody knew Modcomp because, you are one who first produced real-time Unix. Produce joint patents and IPs, and assist in commercialization of the developed products and software. Thank you. I suggest no question. Let's have Victor, who is our PhD student, already 5th year, right? Who is very heavily involved in, he dreams about HPCC. Yeah, he programs every day in the language ECL, so he will tell you more about his research.
Thank you, Borko. Good afternoon, everyone. My name is Victor Herrera. I'm a computer science research assistant and a PhD candidate at Florida Atlantic University. My primary research lies in the fields of data mining and machine learning. And currently, my most recent work is focused on learning from big data, of course. Today, I'm going to share with you my experience on the cooperative project between Florida Atlantic University and LexisNexis, developing machine learning algorithms on HPCC platform. So let's take a look at the big picture of the project. We have on top the source of the knowledge of the machine learning algorithms, but it's been nurtured since late 50s, and it has a peak on the 90s when the integration of computer science and statistics. But the situation right now is that there is not only plenty of proposed machine learning algorithms, but also there are many of them are already implemented in different platforms. But the situation changed due to the impact of big data and the increasing of the computer power. The computer power. This algorithm has to be implemented in a new approach. So in our project, we believe that parallel computer is the answer for this challenge. LexisNexis HPCC platform is ready to work with big data. No, it was designed for that, using his parallel processing computing. So the mission of our program is to contribute to the growth of the HPCC ECL machine learning library. I've been part of this project since summer 2012. My primary role is to develop these algorithms using ECL. So as a part of a team, I had support from both university and industry. From Florida Atlantic University, I received machine learning insights before the project and during the project, as well as receive advice on which classifier has to be implemented first and in which order. From LexisNexis, I received special training sessions on Boca Raton, covering introduction to ECL, Thor, and Rashti, as well as regular advanced ECL and Thor trainings. Probably my teachers are here. Yeah. In addition, during the entire project lifespan, I received continued technical advice from Edin and the group about the implementation itself of the machine learnings. So let's talk about what is the project scope. Machine learning algorithms could imply a very variety of tasks, purposes, and implementations. Our project is focused on, supervised learning for classification from big data. We build programs called classifiers. These programs, given a population that we identify as a population, can tell you after a process for a new observation to which of this subpopulation it belongs. It means these programs learn from data. We call this process learn from training data. This training data has to have a class. In the class, we can see constructors, businessmen, doctors. And through the machine learning algorithms, it delivers a classification model. So later, this classification model can be used to classify a new observation and give a prediction of which class it belongs. So this is a very simple example, but it could be applied in any field. And for example, fraud detections, or even there are a lot of projects right now that using in bioinformatics. They are working with genes, or for any kind of prediction, for forecast, for example. At the moment I joined the project, there was already a library. And it was my starting point in April 2012. It was both supervised and unsupervised learning algorithms implemented there, some of them. So you can see these algorithms were grouped in 4 functions, the big function: classification, regression, clustering, association analysis. But our project is focused here, classifiers. When I get inside the project, it was already open source. So even though it's, I'm sorry, there is no really big difference from the point of view of the open source for this project for another project. We share a library in GitHub. There are many contributors that come from the community, and there is administration. So how it works? You work in your copy. You ask your administrator to review your code. You receive feedback from him. If it's necessary, through comments, you work through this comment. And at the end, it could be merged when the job is done. So what's the difference? The difference really in in this project is the source. The source of the knowledge, as I told you, is machine learning documentation. Sometimes it's not easy to get access to that. I told you that our algorithm from 50s, so we are spending 50 years of documentation on machine learning algorithms. But of course, I had HPCC ECL training, and there is a lot right now. You heard about this documentation and forums on HPCC. There is online courses, forums, even the code is exposed so you can take a look at it at any time. So I'm going to talk about my experience. Even though I have a background as a software developer and database administrator, I never have contact with a data-centric or declarative language before. So at the beginning, I didn't have a clue how it works, how ECL works. And I'm going to tell you about my experience in using 3 aspects: implementation complexity, algorithm complexity, and language knowledge. This is the first stage. I just review code. I review code to understand how the things are implemented in ECL. I understand machine learning algorithms. I started with naive Bayes, one of the simplest ones. Review and then take a look and then figure out how's the big picture, how the classification, all the process, learn process, classification process, evaluation process. At this point, I have only knowledge of transformation, basic transformations and aggregations. Even with this little knowledge, I'll be able to submit my first contribution. I fixed a naive Bayes box, and I improved the performance metrics of the classification itself. The second stage of my learning path was adding functionality. I found a module, it's called tree, that has a function that could partition data into a tree. Later I'm going to talk about decision trees. But it was not a classifier, it was not a complete path for the classifier. It only partitioned the data. So using this and my knowledge on data distribution, incipient at this point, I'd be able to implement my first classifier, decision tree, using gene impurity. And then I extend this to decision tree C4.4 using information gain ratio. Then I realized, oh, I have 2 decision trees, and only I have a one model for classification that it doesn't fit it. So I have to create a family of classifiers. So I invented a new level for that. And so you can use the classifiers through the umbrella of this family, put it different parameters for all of them. Then, after following the path that we created from the beginning and the planning of which classifier we're going to implement, I found I have to deal with KNN and random forest, very, very special classifiers. KNN really doesn't have a model. You just partition the data, and then with the new data, you look for the nearest network to define which class it belongs. And the random forest is not other thing that an ensemble of decision trees. So I have to upgrade one decision tree to many, and then make a majority voting for taking the class. At this point, parallel optimization was really, really necessary. All this path, I did it first with discrete data. And then we figure out, oh, OK, great, you have this with discrete data. Now you have to do it with continuous. a different approach from the same classifiers. So I have to make everything again with continuous, except KNN. KNN is not ready for continuous yet. The next step for the future, and we're not doing that yet, is have mixed data sets. Some real cases have data set with attributes on continuous and discrete. So now I'm going to talk about a little, very simple example to demonstrate how the classification works. I took a very used data set from machine learning. It is called iris. It is a flower. It is based on 4 categories. It are not measured, all the numbers are reals. So based on these 4 categories, they can classify the flower in 3 categories: Setosa, Virginica, and I don't remember the other one, but really, it doesn't matter. The only thing that I want to say is, if you have data that can be represented in attributes, at this point, all of them continuous, all of them discrete, and they have a class final that it belongs, we can learn from that and make a model to predict. So here, I am comparing 2 of the classifiers that we developed. One is decision tree, and the other one is random forest. This is all the code we need. Besides the loading of the data and putting IDs to all the data, take a look. Almost they are the same. The only difference between these 2 is at the beginning, when you are defining which classifier you're going to use, the input of the parameters. After that, is the same path. You learn from the data, you take a model, and then you use this model to classify new data, and then you evaluate your performance. This, for example, is the output for the model on decision tree. Really, the way that we can do all of them is the same path. This is the data structure that for us, a human, but really for the machine is just a matrix. IDs, numbers, and values. We can represent this, any kind of model with this matrix. But anyway, this model in numbers really represents a tree. So this is one of the classifiers that is more easy to understand. It's visual. There are decisions on the values of the attributes, and it takes all the way down until find a final location. So remember, I told you there were 3 types of these flowers. If you follow this path, you take a value anyway. The random forest is the same thing, but multiplied by 100, 200. I don't know how many you need for your job. The thing is, with using random forest, you generalize your decision. Sometimes these decisions are so, we call it overfit. The model is so close to the reality that if you put a different example for that, maybe it won't understand it, and it gives you a wrong answer. But using random forest, you generalize this learning, and your answer is going to be more precise. So I'm not sure if you can really read it, but this is the result. So this is the real class. This is the one that gives you the model after the classification. So for example, in trees, and the first one we got a perfect score. The second one we have one that it was misclassified, and the third one we have 2 misclassified. With random forest, we got a perfect score for all of them. So I'm going to talk finally about the whole contribution of the project. And I told before that we are focused on supervised learning. So Naive was implemented at the moment that we start, but right now it has also a continued implementation. Decision tree is implemented for gene impurity base and information gain radio, both continuous and discrete. Same thing for random forest. The case base, the KNN is only implemented in continuous. And not only these classifiers are the contribution for the project. Also, we got one phenomenon they call cross probability. Sometimes when you put the values on the model, you put a new value that the model didn't take a look before. It's a new model. It doesn't know what to do. So instead of following only one path, you can follow two paths with probabilities. For example, you can say, okay, 40% you can go to the right and 60% to the left, and you keep going, and at the end you're going to have a decision on a class based on probabilities. Also, we have this was necessary. This is the only way we have to compare two different classifications result. This is called the area and the rock curve. So it doesn't matter from which classifier, the result comes. If you have the AUC curve metric, you can compare how well it works. So, summing up, our project was focused on implementation of classification algorithms from big data using parallel processing. We added functionality for naive classifiers, implemented decision trees, KNN and random forest classifier into the machine learning library from ECL. And right now, we are currently evaluating all of these classifiers together, comparing and finding the flawless that we have to improve to make it this faster. Edin, you can go. Thank you.
Thank you, Victor. Let me put this collaboration with FAU in proper frame of reference. In June, 3 years ago, LexisNexis has announced open source, high performance computing cluster, which was designed to solve big data problems. This is basically the time when data-intensive computing started gaining interest. This is the time when scientific community started embracing the ideas advanced by Jim Gray, where he basically recognized that science is entering new significant phase, the phase where new significant scientific discoveries are going to be a result of data exploration. This idea of his is very frequently referred to as fourth paradigm, data-intensive scientific discovery. At that time, he was telling everyone how it is important to have the appropriate platform in order to support everything that is needed by that. National Science Foundation also recognized the importance of data-intensive computing, and it started several programs, funded several programs in the area of computer science and engineering, where they wanted actually to motivate researchers to spend more time investigating capabilities related to data-intensive computing. So this is the time when LexisNexis made the announcement. We knew that we had an excellent tool for data-intensive computing, We wanted to make it available to community, and we wanted to see it used. Now, it turned out that after we made announcements and made press releases and created marketing campaigns advertising HPCC systems, we gained recognition, but we didn't actually have much traction in the acceptance, in actually having people starting actively using the platform. So we recognized that it was important to do something else. We wanted basically to be able to demonstrate to potential users capability of that platform. We also wanted to motivate them to take an effort to learn how to use that, and we understood that we needed to basically help them in that process. We needed to educate them, we needed to provide some support. And basically the idea came that the best way to do that is to start collaboration with universities. Now, as Borko said in his presentation, FAU was a logical choice because FAU is local to our environment. We had close ties with FAU because many FAU graduates actually ended up working for LexisNexis and having very successful professional careers. So this is why we initiated this collaboration process with FAU. On our side, we had Flavio, tireless promoter of HPCC, and on the other side, we had Borko, who, as he told you in his presentation, was very interested in building and expanding collaboration between university and industry in order to actually make the center that he was telling you about, Center for Advanced Knowledge Enablement, stronger. So this is how everything started. Dr. Tagi Koshkovtar, he's a known researcher in the area of data mining and machine learning. He was assigned to be a principal investigator on FAU side on our research collaborative project. So we had meetings with him, and he told us that very frequently when he runs his data-intensive experiments, he has to wait even 6 months until he basically gets his results back. He said that very frequently he has to manually split data and workload, and then he calls favors from his buddies working in different universities, asking them to basically give him access to any spare CPU cycles that they may available. And this is what he has been doing. So based on that conversation, we had an idea that it would be great for him to actually stop using single computer system, and try to use HPCC platform, because this is what HPCC platform has been designed for. Now, the problem was that our machine learning library that we have created was in its infancy. We didn't have enough functionality for him to support all the requirements that he had for his research. And this is how we defined basically the initial project. Victor has been working on, and Victor told you about what he has done. But the main objective really has been to add functionality to our machine learning library, so that whenever the size of the problem exceeds capabilities of a single system, Tagi or any other interested researcher could actually take our platform and forget about having to worry about how to split the work and concentrate on the problem that he's trying to solve. So this is basically why we decided to work on expanding our machine learning library as part of this collaboration. We also realized that we need to actually provide some kind of training to FAU students. We have to educate them on how to use HPCC systems. We have to get them to like the platform. And this is why we started actually collaborating and working with Borko on creating data-intensive computing class that we would offer through FAU. Now, creating class of that type is not a simple matter, because this is very complex subject, and you can really address it in many different ways. You have to worry about prerequisites for the class. You have to worry about satisfying academic requirements of institution that is offering that class. And basically, lots of issues needed to be resolved before we would actually proceed with delivering that class. So what did we do? We Googled to see what other people have been doing in this area. And what I found was a report written by Professor Edin about her experiences introducing new technology in a classroom, and this is dated 2001. This is the time when she felt the need to introduce the course at a university talking about complexities of cluster computing. She basically collaborated with her colleagues working at different universities, some in the United States, some in Australia, and they together designed the class, the course, and delivered it, and then created this report together to share their experiences about that. Professor Edin is now chair at Computer Science Department at Clemson University. I believe she has been working on creating an equivalent course about data-intensive computing. And I thought it would be great if she could kind of create similar collaboration to this, creating this data-intensive computing course, because other members of HPCC academic community apparently are also interested in actually creating course and educating their students about that. I have to tell you that I'm not aware of how much time I have. 5 minutes, okay. So I continued searching the web for the information related to the classes, and I found a variety of offerings related to data-intensive computing. The first one offered was by University of Washington. They are co-located with Google, and they apparently have very close ties to Google, so they have put together in excellent class the tools that they have used for demonstration in that class was Hadoop, which is not unusual. This class has been recorded at the time, and I really liked it. I watched it, and I would basically suggest anyone who has any interest in this to take time and watch it. I have also found other types of coverage of this subject. Some, for example, I believe Illinois Institute of Technology offering was very theoretical with very little practical hands-on work being associated with that, and I didn't think that is basically the appropriate way to approach that subject. So my preference would be really to have balanced approach to that. I also looked up massive open online courses offerings related to that, and I have found a number of courses, but those are mostly related to data science. Those classes are basically about very specific subjects related to data science. They are excellent classes taught by excellent professors teaching at excellent schools. So if anyone has any interest, I would really highly recommend taking those classes. Now, there's an interesting thing. Harvard Business Review magazine has published an article recently saying that data scientist is the sexiest job in 21st century. So it looks like that a data scientist job really is a hard job, and it is not surprising that many universities are actually taking time to help their students develop skills needed for data science. What I found interesting also is the fact that those classes don't actually deal with preparing data for processing as part of data science operation. Because in order for you to be able to extract any information out of your data, you really have to prepare your data. And Drew Conway, I believe he has created a Venn diagram defining skills required by data scientists. And one of the 3 important skills that he has identified is a skill for data hacking. This is how he called it, but this doesn't have any derogatory meaning. This really means that you have to know how to prepare your data for appropriate processing. And interestingly enough, our platform has been designed to do that job very efficiently. So our preparation for the course has been completed sometime in 2011. The class was delivered, and Borko mentioned that he attended several classes and he was impressed with the presentations that students have made. Now, I would just like to make a short comment. One of the problems that I had to deal with setting up that class, and I'm saying that because, again, of the fact that I know that people from other universities are also, who are looking at delivering or creating data-intensive computing class, are also thinking about maybe using HPCC systems as a tool for that class. The problem was where to actually host the cluster to be used in a class. And it was very convenient for us to have to deal with the College of Engineering at FAU, who had its own cloud. And basically, we had very good collaboration with them. So we worked with them for them to identify and isolate a number of nodes. And then they gave me administrator privilege for those nodes. And because of that, it was very convenient and easy for me to set up a cluster of the size that I needed for the class. And in addition to that, I made it also possible for students to go through that process of configuring cluster, because apparently having hands-on experience building something is very valuable experience that students like. I am out of time and did not cover everything, so I don't know what my options are now. Maybe 5 more minutes? Okay, I will go through that. So quickly, every student in a class had to create a data-driven application and present it to the class. This is what Borko attended and he was impressed with. I wanted to show you 2 projects that have been done by students. One was called Save, See, Save, and Skip. The idea really was that we don't have time to watch all those series on TV. We would like to know what's worth watching. And these students actually decide to do some sentiment analysis in order to figure out what programs people liked and what programs they didn't like. So she used classification to do classification and basically created very successful project. And I believe that many of LexisNexis people had the chance to see that and even to see the advanced version of this that she has created after completing the project. The other interesting project is an extension of the project that Borko mentioned in his presentation, asset identification using image descriptor. This is the project that student has done on completely separate, in completely separate environment, and he suggested to try to use HPCC platform actually as a matching platform. So the idea is you extract the feature from the image, and then you have to try to match that feature with the existing stuff. That was also very, very impressive project. So this is the reference to data data scientist skills that one have to be real data scientists that Drew Conway created. It was interesting thing. He basically gave very good speech about that, but it was funny when he described how important it is to actually acquire all the skills, because if you are missing any one of them, things could actually go the wrong way. So he was explaining, not in these words, but I will kind of paraphrase, hacking skills. These are the skills that you have to be able to process your data appropriately. So since our platform has been designed to do something like that, I would say, well, imagine you have data and you have HPCC platform, so you collected all the data and you cleaned it up and prepared it for processing. So let's say that you have all machine learning library functions that you need for your data scientific research. Substantive experience is basically the knowledge that you have about the subject so that you can actually ask some questions and try to gain, to extract information from data about. So you do all of that and you get some results back. And then, if you don't have those math and statistics skills, you may not be able to interpret those results appropriately. You can actually misinterpret them completely, and this is what he has called danger zone, and this is what he also said. This is where lies, damn lies, and statistics come from. You don't know statistics, you can actually make up any story you like. So to end my presentation, the objective of our collaborative effort with FAU was to overcome limitations imposed on tools running on a single computer so that we can actually make data-driven scientific discovery easier to people. We have many people actually contributed to that. Professor Borko, Furht, and Flavio made it possible for that collaborative effort to start. The team, Tagi Koshkovtar and Victor and Miriam, have been working very hard. Victor really has added lots of functionality to our machine learning library. And my job was to have fun teaching that class, and I really had fun teaching that class. I would also like to recognize Richard Taylor and Fernando Uceta here, because they made my job so much easier. You know, when you are deciding what kind of textbook you want to use for the class, one of criteria that at least I have is that this book comes with a lab manual. This is instructor-only manual. This is the manual that actually has exercises that are very well suited and go together with the topic that you want to present. And they give you answers to difficult questions so that you can ask them at the exam and don't worry about not knowing the answers. So Richard Taylor has been a trainer of HPCC and ECL for a long time. He has developed an exceptionally well training material set, and he has shared that to me. I use that as that supplemental lab manual. Without it, my life would have been much more difficult. I told you that I have worked with FAU IT department to basically carve out and create this cluster. Most of the time, this process ran smoothly. Once in a while, we would run into some problems, performance issue and such. Fernando Uceta is a seasoned operations engineer who knows operations of HPCC platform inside out, and he's a very nice guy, and he's willing to help you out whenever you need help. So he was there for me whenever something would go wrong with the cluster, and I'm very thankful for that. I'm bringing those two things up because whoever is thinking about offering or putting together data-intensive computing class using HPCC as a tool, you can count on Richard Taylor and Fernando Uceta, I'm sure, if you ever have any need. Thank you very much, and I'm sorry I overstepped my welcome.
Thanks, Ed. All right. Thanks, Borko, Victor, Edin. I love that quote. I think I'm out of time and I don't know what my options are. I gotta get that on a t-shirt. All right. So FAU, yeah, Borko was really interesting, the slides you had with all the different courses that you guys now offer in technology, mobile computing, big data. So I know our LexisNexis and lots of companies are looking for students with those skills coming out of school. So it's great that FAU is kind of taking the lead on offering that range of classes. And I think we'll hear more about that this afternoon from our other speakers from other universities. So we are at break time. We're running a little behind schedule, but we will not take away from your break. It is 2:25. We will reconvene in 15 minutes at 2:40.